Welcome students. Today we will be covering the topic dynamics of non-uniform circular motion. When a particle is moved in a circle under the action of a torque, it acquires an angular acceleration. Angular velocity of the particle and hence its angular momentum will change. Also, the linear velocity, linear momentum and kinetic energy of particle will change. Such a motion is therefore called non-uniform circular motion. Motion in a vertical circle. To understand the dynamics of non-uniform circular motion, let us consider the motion of a small body tied to one end of a string and whirled in a vertical circle. At any time, let the body be at P at angular position theta, as you can see in the picture. The forces acting on the body are weight mg of the body acting vertically downwards, tension T in the string acting along PO. Now, mg can be resolved into two rectangular components. mg cos theta opposite to T and mg sin theta along tangent to the circle at P. Net force on the body at P acting along PO is equal to T minus mg cos of theta. This should be clear from the diagram itself. You can see T and mg cos theta are acting opposite to each other. So net force is given by T minus mg cos theta. Now this must provide the necessary centripetal force, that is mv square by r, required by the body, where v is linear velocity of the body at P. Therefore, we may write T minus mg cos of theta equal to mv square by r. From here we get T equal to mv square by r plus mg cos of theta. T will be minimum when cos theta is minimum, that is cos theta is equal to minus 1 or theta is equal to 180 degree. This will happen when the body is at the highest point H. So we can write down T minimum, if I represent it as TH, this will be equal to m v square by r. Let the velocity at the highest point be given by vh square, vh. So obviously we'll get m vh square by r minus mg. Cos theta is having a value of minus 1, so you get minus mg. This is the value of minimum tension. Now the body will move along the vertical circle only when T minimum is greater than equal to 0. This means if T minimum is less than 0, the string will slack and the body will fall down from H instead of moving in the circle. Hence, for completing the circle, for completing the vertical circle, which is also called for looping the loop, T minimum is equal to and that is greater than equal to 0. So we can write down mvh square by r greater than equal to mg, or vh should be greater than or equal to gr. Therefore, minimum value of velocity at the highest point is root over gr. Now, by applying law of conservation of energy, total energy at L, that is the lowest point, is equal to total energy at H, that is the highest point. So in order to find out the total energy at the lowest point, the energy is totally kinetic, so you will write down half m. If suppose at the lowest point the velocity is vl, then half m vl square, and height is 0, so it is entirely kinetic in nature, whereas in the highest point the energy will be both kinetic and potential. So kinetic energy will be given by half m vh square, and for potential energy mg, and height will be equal to the diameter, that is 2r. So now, using the previous equation for vh, we may write down half m vl square to be greater than equal to half m, in place of vh square we can write down gr plus 2mgr. So you get vl square to be greater than equal to 5gr, or vl is greater than equal to root over 5gr. Hence, for looping the vertical loop, the minimum velocity at the lowest point, should be equal to root over 5gr. Now, we have already obtained an expression for tension T that was equal to m v square by r plus mg cos of theta. For maximum value, cos theta should assume a maximum value, and that is equal to plus 1, that is theta is equal to 0. So maximum value of tension will be at L. So this should be equal to TL, and that is equal to m VL square by R plus mg, and cos theta is equal to plus 1. So when the body is looping the loop, VL is greater than equal to root over 5gr. So therefore we can write down T max, that is equal to TL, that will be greater than equal to m by r times 5gr plus mg. So we can write down TL to be greater than equal to 6 mg. So this will be the maximum value of tension at the lowest point. While the body is moving in a vertical circle and the string becomes horizontal as at M, theta is equal to 90 degree. So total energy at M will be equal to total energy at L. So we can write down half M Vm square plus mg, and this is equal to mgr, that will be equal to m half m vl square. So we can write down half m vm square to be equal to half m vl square minus mgr. So using the previous obtained values, we can write down half m vm square to be greater than equal to half m. We already know that vl is greater than equal to root over 5gr, so instead of writing vl square, we can write down simply 5gr minus mgr. So you get half m vm square to be greater than equal to 3 by 2 mgr, or we get Vm to be greater than equal to root over 3gr. Using this value for Vm and theta to be equal to 90 degree, we can get tension at this point to be greater than equal to 3 mg. For this, we simply need to substitute in the expression for tension that we have obtained earlier. So now we can say, after the study of motion of a body in a vertical circle, we can conclude that for looping the loop, VL should be greater than equal to root over 5gr. For oscillation, that is theta is less than 0 and less than equal to 90 degree, this equation should be satisfied. This follows from energy conservation actually. Half m VL square is greater than equal to mgr, so VL should be greater than less than equal to 2gr, root over 2gr. So obviously velocity becomes 0 before t vanishes. That is why the body oscillates. Third, for leaving the vertical circle, that is, for this condition, we have root over 2gr less than VL less than 5gr. At this point of leaving the circle, t is equal to 0, but velocity is not equal to 0. So obviously, after understanding the different concepts regarding motion in a vertical circle, we should also discuss some practical applications of motion in a vertical circle. When a bucket containing water is rotated in a vertical circle with a velocity at the lowest point, VL greater than equal to root over 5gr, water shall not spill even at the highest point when the bucket is upside down. If the bucket is whirled slowly so that mg is greater than mvh square by r, where h is the highest point, then a part of the weight shall provide the necessary centripetal force, that is mvh square by r, and the rest of the weight of the water, that is mg minus mvh square by r, causes some water to accelerate downwards and spill. Only this much water shall leave the bucket. Similarly, we can discuss one such situation that a pilot of an aircraft can successfully loop a vertical loop without falling at the top of the loop being without belt when its velocity at the bottom of the loop is greater than equal to root over 5 gr. Let us consider one more situation. In a circus, a motorcyclist is able to perform the feat of driving the motorcycle along a vertical circle in a cage. The motorcyclist does not fall even at the highest point when his velocity at the bottom of the cage is root over 5 gr. It should be greater than or less equal to root over 5 gr. For this, to acquire this velocity at the lowest point, that is at L, of the vertical loop of radius r, he has to roll down a vertical height h. So we can use the equation v square minus u square equal to 2as. U is 0, a is equal to plus g, and s is equal to h. So we get v square minus 0 to be equal to 2gh. So v is equal to root over 2gh. So for looping the loop, this velocity v acquired at L must at least be equal to root over 5gr. So we can write down root over 2gh to be equal to root over 5gr. So very easily we get 2gh equal to 5gr, or h should be equal to 5r by 2. So acquire the velocity at the lowest point L of the vertical loop of radius r. Thus motorcyclist has to roll down a vertical height given by 5r by 2, where r is the radius of the circle. So this will be all for today's discussion. Thank you.